you very much. I would like to thank Lewis and Simon for the organization and for giving me the opportunity to speak. So today I would like to present a joint work with Tristan Bozek and Maxime Ferron on double Poisson vertex algebras. So I will give a precise definition later in the talk, but let me first say that roughly this double Poisson vertex algebras is an associative, unital associative, in general non-commutative differential algebra. So which means it comes with a derivation equipped with a bracket, let's say a double bracket, which is compatible with the product coming from the algebra structure and the derivation. So as you can expect, this is a vertex analog of double Poisson algebra, and at the same time, this is a non-commutative version of Poisson vertex algebras that already appeared in this conference. So the aim of the talk is essentially to construct interesting examples. So maybe I should say that the definition is, the notion is quite recent. It was introduced by Desole, Katz, and Valéry in 2014, motivated by the study on non-abelian integrable partial differential equations. So yeah, the aim is to produce an interesting example of such structures. So construct example of double Poisson vertex algebras using functorial constructions. So in particular, I'm going to use a jet algebra constructions. So let me explain the general idea, and I will go back to detail after. So the idea is the following. If you start with any associative algebra, so a finite type, so everything will be over C in my talk. All right? So the jet algebra construction produce a differential algebra that satisfy a certain universal property. All right? And the key point is that if A is a Poisson algebra, then you get a Poisson vertex algebras. And now if A is a double Poisson algebra, then you get a double Poisson vertex algebras. And now if you use the representation functor, so the representation functor associate to any associative algebra a commutative algebra. So here I need to fix a positive integer, which is the coordinate ring of the affine scheme of representation, of n-dimensional representation. So this is the algebra of matrices with obvious relation. And here, if you start with a double Poisson algebras, you get a Poisson algebra. So you can do also the jet algebras construction here. And what we want to explain is, first of all, that this diagram commute. And from this construction, you can also consider related constructions such as Poisson reduction or Hamiltonian reduction. So I want also to consider related construction. So Poisson and Hamiltonian reduction, and also consider connection with vertex. So this is essentially what I want to explain. So let me start with the finite type setting. So I want to recall some facts on double Poisson algebras. So the notion goes back to Vandenberg. And in fact, it was also studied in slightly different terminology at about the same time by Paul et Beauvais. fading through. So one motivation was to study the Poisson structure on quiver varieties and multiplicative quiver varieties from non-commutative setting. So a naive observation is that there are only few non-commutative algebras equipped with Poisson bracket, except the commutator of element. So in order to get a more interesting non-commutative version of Poisson algebras, the idea is to use this representation functor. And the philosophy is that A has a nice geometry if the representation scheme has a nice geometry. And the definition of double Poisson algebras on Vandenberg is designed so that if A is a double Poisson algebra, this is a Poisson algebra. So the definition is the following. A double Poisson algebra is an associative algebra. I will use double letter in the double setting to do that. Equipped with a linear map from A times A, and here the novelty is that the image is A times A. And it satisfies the similar axioms for Poisson algebras. So in particular, you have skew symmetry, Leibniz rules. So because of the non-commutativity, you have to specify left and right and Jacobi identity. So for example, the skew symmetry is written as follows. You have that this is this, where this is the involution for the tensor product. Okay, so I don't write the other axiom, but you can imagine. And the key point is that if A is a double Poisson algebras, then the representation algebra is a Poisson algebra, and the Poisson bracket is entirely determined by the double Poisson structure. So this is the generators of the coordinate ring. So you have something like that. Maybe I will be wrong. X. This is a Schroeder notation. Okay, so this determines entirely the Poisson structure. So let me give some examples. So I start with the easiest one. Let's consider the free algebra generated by one variable. It's actually commutative, but it does not matter. You can equip with a double Poisson bracket like this. So this gives you a double Poisson structure, and here the representation scheme is just a space of n-dimensional matrices that you can identify with the dual, with the usual Poisson structure. The standard Poisson structure. Okay, so similar spirit. Now let's consider with two variables. So it's not anymore.
Sorry, you said it a few times. What is AN? How do you get it from A?
Ah, sorry, I didn't say. Sorry. So AN is a coordinate ring of the affine scheme of representation that parameterize n-dimensional representation of A. If you want a precise definition, maybe you add relation. So this is generated by elements like this, and the relation you want, it's a coordinate of matrices. And you want also linearity and so on. All right? So you can view it as an algebra of matrices. Is it fine?
Yes.
Yeah.
Yeah,
Sorry.
Thank you so much.
Sorry. Yeah. Yeah, so here it's easy to see that the space is this, and then you have to understand the Poisson structure. It's just the point, yeah. And here now, in the same spirit, so you don't need the Poisson, double Poisson bracket to see what is the representation scheme, but I give together the examples. So, and then you have something like that. So here what you get, as a space, you get the tensor product of mat m times mat m as a space, but the Poisson structure you can identify with the cotangent space of mat n, and you get the Poisson structure coming from that. So a priori you get the tensor product, but as Poisson variety, it is this one, with the Poisson product coming from the symplectic structure. All right. You can also localize this example. So I don't write here the Poisson bracket, but you can deduce from this. And here you get the cotangent bundle of GLN, because you allow to invert the second variable. So, etc. And one can actually generalize this example from double quivers. So let's consider a quiver, finite set, and then I consider the double quiver. So if you have a quiver like this, you add inverse row like this, and then the path algebra of this double quiver has naturally a structure of double Poisson algebras. This is the path algebra. So the Poisson bracket, the double Poisson structure is given as follows. So maybe I should write like this. So it's 0 is B is not A star, and it is this. I will explain the notation. So first of all, here I write this is a head, and this is the plane of my arrow, and epsilon is the map which is 1 if A belongs to the original quiver, and -1 on the right. Alright, so this is a natural generalization of this example, and the point is that this is double Poisson algebras, and the representation space here. So here you have to take a dimension vectors, not only an integer. So here you fix a dimension vectors, and here it's isomorphic to the coordinate ring of the cotangent bundle of the representation of the original path algebra of the original quiver. Alright. So this is in fact a particular example of what Crowley-Bové, Tinkoff-Ginsburg call non-commutative tangent algebras. Alright, so this is for the example, and now I would like to take into account of the action of GLN, because GLN naturally acts on the representation scheme by conjugation. So yes, so far we have this functor, and here GLN acts by conjugation on Rup n and so on the algebra. So of course you need to take a product of GLN in kind of double quivers, but it does not change. And then, no, sorry, I would like to make a picture. And then from this you can, so it acts by Poisson automorphism, and then you can consider the Poisson reduction. So this gives you a Poisson algebra. You can also consider Hamiltonian reduction if the action is Hamiltonian. If the action is Hamiltonian. So and then, as I said in the introduction, if you do the jet algebra construction, here we will see that we go to a Poisson vertex algebra. Okay. So the aim of the talk is essentially to complete that cube. So I want to explain what is the reduction in the other part and how to complete the jet algebra construction everywhere. This is the aim. Okay. So here, this part is known by Van den Berg. So I will start by explaining how to construct analog of this Poisson reduction, and then the point is to explain this part, and the last corner. So here I can explain now because so what you do, so you can assume double Poisson algebra, but it is slightly more general. But then you can consider this quotient that already appeared in Eric's talk. So this is a vector space generated by commutator. And what Van den Berg observed is that the Poisson structure here is entirely determined by some Lie bracket here. And then you use the trace map to make the diagram commutative. So here this is a trace map. So which gives just this, and this is obviously invariant, and this map descend to the commutator, of course. So it's well defined. And what is the Lie bracket here? I explain here. So the Lie bracket, so it's induced by the multiplication over your algebra, and then you compose with double bracket. Let's write a sharp the image of A in. So this is usually written at H0. All right. So now you can take the image here, and this is your Lie bracket. No, sorry, I put. So this is how it works here. All right. So now I would like to discuss the vertex algebra setting. Any question about this known part? The order. Yeah. So second part is about Poisson vertex algebras and double Poisson vertex algebras. So let me first give a definition of Poisson vertex algebra. So what is a Poisson vertex algebra? So this is a commutative differential algebra. So this just means that it is equipped with a derivation. I don't ask the square is 0. The terminology is just like that. Equipped with a linear map. maybe I call V here. We are in the vertex setting. So here we go to the algebra of polynomial with value in V. All right, and we get what is often called a lambda bracket. And here it satisfies usual axioms on Poisson algebras, except that you have to take into account the derivation. So here the axiom, there is a new axiom which is the sesquilinearity. We tell you that how it behaves with the derivation. Sure. Something like that. And then you have the usual axiom, Leibniz rules. You have the skew symmetry that I don't write, but you can imagine. Jacobi, etc. All right. So, so this was introduced. This was intensively studied by Katz, Desolé, and other people, motivated by the integrability of partial differential equation, but it is also a very important notion for vertex algebras themselves, not necessarily commutative. Another viewpoint is to say that this is a commutative vertex algebras equipped with a richer structure. So let me give interesting examples of Poisson vertex algebras. In fact, to construct example is you can use the jet algebra construction, as I mentioned. So if A, so for the moment, let's say commutative algebra, maybe I give a definition. This is a unique up to isomorphism differential algebra which satisfies a universal property that homomorphism of algebra from A to any differential algebra is the same as the homomorphism of differential algebra from this jet algebra to B. All right. So another way to define this slightly more geometrically, equivalently, this is a unique algebra what satisfies that the homomorphism of algebra from this algebra to R is the same as the homomorphism of algebra from A to the ring of formal series over R. For any C algebra R. Alright, so in this talk I rather want to use this viewpoint. So in this viewpoint you see that the corresponding scheme, the C point of the corresponding scheme correspond to the point of the point with value to the formal series of spec A. And in fact, the geometry of this object gives you very interesting information about the singularity of spec A. So I don't talk about this aspect today, but this is of independent interest. So for example, if A is just a polynomial ring, then this is just the polynomial ring with infinite variable. And if there is a quotient here, you can just take the ideal generated by the image. You have a natural derivation here, and then you expand here. All right. So this is the general setting, and now the fact observed by Tomoyuki is that if A is an algebra, a Poisson algebra, then the jet is a Poisson vertex algebra. So this gives you very interesting examples. So if A is Poisson, then there is a unique Poisson vertex algebra structure on the jet algebra. Of course, you want it extend the Poisson algebra, such that this is the Poisson algebra for all AB, which naturally embed the jet algebra. All right? And the motivation here comes from vertex algebras, because now I want to explain that any vertex algebra produced canonically, in a canonical way, interesting Poisson vertex algebra. So second examples, I want to explain that any vertex algebra is naturally filtered. So this was obtained by Lie. So this is the so-called Lie filtration. And the key point is that the corresponding graded vertex algebra is commutative. And as in the classical setting, when you have graded commutative algebras, you can expect a richer structure. And this is indeed the case. So this is, in fact, is a Poisson vertex algebra. It's naturally a Poisson vertex algebra. And on the other hand, if you remember Tomoyuki's talk, you can associate the associated variety or the associated scheme. And as Tomoyuki explained, this is a Poisson scheme. And so, as I mentioned before, the jet scheme, so the corresponding jet scheme, is also a Poisson vertex algebra. So you have also canonically associated with this, so rather the coordinate ring of that, or if my notation is better to write like this, I recall that the RV is a coordinate ring of that, is a Zoo-C2 algebra. Okay? So let me give examples where actually these two things coincide. In general, you just have a surjective Poisson vertex algebra morphism between the two. So I would like to give an interesting example for my purpose. So of course you can expect to understand V from these two objects, which are more geometric. So example, let's consider the affine universal affine vertex algebras that already appeared. So here I want to assume a G reductive. All right, so I recall that this is defined as follows. So this is a affine class-model algebra associated with this. And this is a one-dimensional representation of this. This was already explained. And you see, if you want to understand this space, using the PBW filtration, you see that as a vector space, it's isomorphic to that. So, okay, the PBW filtration is not exactly the Lie filtration, but it turns out that as a graded algebra, it gives the same. So let's think of the PBW filtration. And if you think of this, you get the symmetric algebra of that. And this, you can see that this is canonically isomorphic to the jet algebra of the coordinate ring of G star. All right? So here you associate an element like this for positive n. You associate the derivative of x for x in G that you view as an element here. All right? So, and if you remember in Tomoyuki's talks, this is exactly the Zoo-C2 algebra of this algebra. In fact, the associated scheme is exactly this one. So in this case, you get that this is exactly the jet of the Zoo-C2 algebra. in the case of G is equal to GLN, this comes from a double Poisson structure. So you can expect that this comes from also a double Poisson structure in some sense. So this is what I want to explain after. So let me give another example. That also already appeared. So let's consider the vertex, not like that, the vertex algebra of Carroll differential operators on Cn. So this is a beta gamma system of rank n, and here it is known that the corresponding graded algebra is isomorphic. So maybe I should first say that the zoo-C2 algebra is a coordinate ring of the cotangent bundle on Cn. And in fact, in this case, you also have that the graded algebra is isomorphic to the jet of that. So this is another example where you have the isomorphism. So this is a particular cases of CDO or smooth affine variety that were introduced independently by Malikov, Schechman, Ventroff, and Bellinson-Drinfeld. And I would like to consider another example similar to this one. I would like to consider the vertex algebra on CDO on G. So here G is reductive. And this has an explicit description as follows. So of course G is a V algebra. G. And here you induced from this here. And here GT acts by left invariant vector field on the coordinate ring of the jet of G, and one acts as identity. Okay? So, and here also you have that the graded vertex algebra is isomorphic to the jet of the coordinate ring of the cotangent bundle of G. So this example is interesting also because for G is equal to GLN, this also comes from a double Poisson structure. So naturally we want that, so this has a Poisson vertex structure, but we would like to say that this comes from a double Poisson vertex algebra structure. So let me now explain what is double Poisson vertex algebra structure. So any question about this example? Okay, so I'm not going to give a precise definition because, as you can imagine, the definition is a mixture between double Poisson algebras and Poisson vertex algebra. So is an associative differential algebra. So it's the same, it's a derivation in the non-commutative sense with a linear map. So this, maybe V. Okay. So as in the double setting, you have a tensor product, and as in the vertex setting, you have a parameter here, and the natural denomination is like this, and plus all axioms you can imagine. And you mix all definitions, so you have the six-square linearity, like for Poisson vertex algebra and the other things. Leibniz rules, so left and right, skew symmetry. and Jacobian. So let me give just one example. So let's consider the free algebra generated by infinitely many variables, like this, and with Poisson bracket. So it's just an extension of the previous example. Something like that, but you can add a parameter here for some C in C. All right. And so I would like to now extend this jet construction in this setting. So this is easy. It just to adapt the definition of jet algebra, but in fact it's not really required to be commutative in the definition. So if A is any associative unital algebra, then define this algebra to be generated by the symbol like that. And with relation, you need to make a differential.
In the top word, do you add standard vertex algebra axioms on?
Sorry?
So on the top word, you define the DPVA. Where's the vertex algebra?
This is not a vertex algebras a priori. What I want to say is that the representation functor gives you a Poisson vertex algebra. So applying the representation functor, you will get a real vertex algebras.
Vertex Poisson.
Yeah, vertex Poisson algebra. But this is in particular vertex algebra. Yeah.
Okay, so there's no like state operator math or anything?
This is one hope. So it will be nice, this is, I will comment right after, to have a double analog of real vertex algebra, so that the graded algebra give you a double Poisson vertex algebras. But so far, this is defined purely in the non-commutative setting from the double Poisson algebra structure, and there is no analog of vertex algebra as I explained in this picture so far. But this is one thing we want to do. Yeah. Thanks for the question. So yeah, so the relation, of course, you want the linearity, but maybe what we want, of course, it's a Leibniz. So okay. So plus linearity, etc. So you impose some relation and you get your candidate, and the point is that this algebra verifies the same universal properties, but in the non-commutative setting, that this is the same as the homomorphism of differential algebra for any non necessarily commutative differential algebra. All right, and of course, the observation is the analog of Tomoyuki's result, is that if A is double Poisson algebra, then this is a double Poisson vertex algebra, which extends naturally the bracket. Okay. So everything is fine, and the first picture I drew is correct. Everything commute with the representation functor. So representation functor was already introduced by Desolé, Katz, and Valéry, and so everything commutes. So precisely, I would like to comment what you ask, because I would like to go back to these two examples in the GLN case. So I want to make the picture in this example. So assume G is GLN. All right. So what?
I have a quick question. So if I take a double Poisson vertex algebra and I only just look at like the zeroth coefficient in the lambda bracket, does that just make it into a I forget the differential and I only keep the.
Yeah, if you so this is of course when I wrote here this is A, and if you forget the differential, you get of course double Poisson algebra. This is your question. Yeah.
Yeah. So this is just the left adjoint.
Yeah.
Great. Thanks. Good.
Exactly. Nothing subtle. So I would like to make the picture here. So what we did, I want to draw like this. So let's consider this example. So here, if I consider the graded algebra, I get the jet of this, and here if it comes from this, and here I explain that this comes from the very simple double Poisson algebra. So by the way, you notice that the double side is usually much simpler than the Poisson side. So this is the motivation. And here you have the jet of that. Everything commutes here. And here I would like to complete the cube using the zoo functor. So you can take the zoo functor. Here you get the enveloping algebra of GLN. And everyone knows that if I take the graded algebra, I have this. In general, this does not commute. If you do Gre and zoo and so on, it does not necessarily commute, but in the universal examples I consider it commutes. So a natural question you ask is how to complete the cube. So this picture suggests that this has a very rich structure coming from double Poisson vertex algebra. So it's natural to expect something here and also something here. But because of the rigidity of vertex algebra, it's probably easier to try to understand this corner rather than this one. I don't know.
So that one is not known?
That one is not known. And it's suspected that this is even harder than this. Because of the rigidity of vertex algebras, maybe we can try to hope at least this example. So the second example we consider is very similar. Everything works well. It was this one here by a result of Tomoyuki and collaborators. It's more general than this, but here the zoo is the algebra of differential operators, which leads to the coordinate ring of cotangent bundle here. And here it comes from this double Poisson structure. And here also you have the jet. And here again you can wonder what are the other corners. So I would like to make a more precise first problem. So of course we cannot expect such things for all vertex algebras. So assume the condition that appears in Tomoyuki's thought that Gre V is isomorphic to the jet of the zoo's algebra. So this is expected to happen for vertex algebras coming from 4D to D duality, as we saw yesterday. And that RV comes from a double Poisson structure for some double Poisson algebra A and some N. So can we describe what are double analog of V, and you can ask also zoo of V. So this is the question. Okay. So now I would like to discuss the other the Poisson reduction and Hamiltonian reduction. So for simplicity, I explain only Poisson reduction, and I will explain how to adapt after. So if you remember, my first cube is different than that one. I would like now to discuss right face. So you remember we had this. Now I want to consider, so this we already discussed. Okay, and now we did the jet. Yeah, I would like to discuss this problem. So here, some technical problems happens because invariant of jet does not coincide with the jet of invariant. So I have to explain how to. So this has nothing to do with double setting, but it is of independent interest. So this is my third part, arcs and invariants. Yeah, to explain what I want to do, if you start with a double Poisson algebra, you have the jet of that, and then you can take the representation functor, the representation algebra. All right. So a priori, GLN acts on this as usual. But if you consider the invariant with respect to that, this is too big. Too big if you compare with the jet of the invariant. All right, if you do, what I want to consider is a jet of this. But this is very big. And of course, what is more appropriate is to consider the arcs of this, of course. So this is the first thing. So what I want to consider is rather this. But now another problem is that is in general not isomorphic to the jet of this. So I don't want to, this is in fact a very
Invariant by jets.
yeah, sorry. And anyway, this is, we don't really care about this setting. I want to make more general setting. If you have an algebra and imagine G acts on the spec, well, let's say on A as Poisson automorphism, this is in general not true. All right? So what we have, we just have that the inclusion, so this is Poisson, because I assume the action is Poisson. It induced algebra morphism from this, and the image is in the invariant space. But this morphism is in general neither surjective nor injective. So for instance, if G is finite, it is not surjective. And so Andy Linshaw and collaborators works a lot on this topic. So this is a very subtle problem. So there are interesting examples where it's true. But the third problem we have is that in fact, even if G acts as Poisson automorphism, the jet of G doesn't need to act as Poisson vertex algebra morphism, automorphism. This is a bit a problem because we want to make everything functorial. So at least we would like that this is a Poisson vertex algebra. So this is hopefully the case. I don't explain the detail, but I just state. So third problem, even through G acts as Poisson automorphism, this is not, does not act as Poisson vertex algebra automorphism in general. But nevertheless, we prove the following result is that in this situation, this is still Poisson vertex subalgebra of the jet. So this is quite nice, and so to make the picture here, you have to consider the jet. This does not commute, so here you have to use the morphism J. So here you do the Poisson reduction and just compose, and then if you do that, it's correct. All right. So let me give some example where this isomorphism holds.
In that even though comment, like, can you still say something about like normally you'd expect it's like compatibility is something about like different, like there's the compatibility is like mix the modes somehow.
Yeah. In fact, what I want to say is that, for instance, so in fact, assume that G is connected so that the action is given by the Lie algebra structure. Okay, so what we, if it were a Poisson vertex algebra morphism, in particular, it should it be compatible with the derivation. But we don't have that. But of course we have this. It's not what I want to say. What I want to say is, imagine the action of the Lie algebra of that. Okay, it's rather this I want to say. So this is in the Lie algebra of my jet. So this does not commute with the derivation, but you have a shift. I forgot the sign, but it's not so important. You have something like that. So even if you have this extra term, so this is not a problem, because if A is killed by all elements by this is still invariant. And this is the same with the nth product. This is how it works. So it's not a big problem, but it's just not so trivial. Yeah.
Yes.
Okay, so let me give yeah, so I just give one example, and I refer to on this work for more examples. So I give one example, a famous example. If G is reductive, so everyone knows that this is a polynomial algebra, and so you can consider the jet of this, and beautifully, this is the jet, the invariant of jet. So this was obtained independently by Rice, Tovel, and Levinson. So this is very important in representation theory, and it appears also in the picture if you take Poisson reduction in my cube for the Ln. Okay, so I need to now discuss the last corner, of the cube. But this is quick. I just explain what we need to consider. So what we need to consider is first a variation of Crowley-Beauvais Vandenberg H0 structure for double vertex Poisson algebra, and this was done by Desolé, Katz, and Valéry. So what I want to say is that V is a double Poisson vertex algebra. You have Lie vertex bracket on it. And similarly to what's happened in the double Poisson case, using the trace functor, it's commute well. But in order to make our cube commuting, we need to consider a variation of this statement using a subspace of the jet algebra. So this is the only thing I want to explain, and then I want to discuss more open problem. So let me try to be slightly more precise. You have this is maybe not necessary I explain. So now what I do is the following. So let's start with the double Poisson algebra and consider this subspace of the jet algebra that we defined as follows. So this is a vector span generated by symbol like this for A and B and K positive. So this is a priori a subspace of the jet of A. All right, and then you have a Poisson, you have the Lie Poisson structure coming from that, and then the cube commute with that. So maybe I just finish the cube. So can I see something? Yeah. So here. Maybe it's fine. Okay. So here you have the jet here, and here to complete the cube, you need to consider H0 of this space. And here what you consider is also the trace. And with this construction, everything commutes well. This is this is the conclusion. And also, so the conclusion is the cube commute. So everything works for Hamiltonian reduction. So maybe here I need to explain what is a non-commutative moment map. So non-commutative moment map is just an element of A such that the bracket of mu with any element of A satisfy this. And of course the definition is designed so that the corresponding evaluation map, like this, is a moment map for the action. Usual moment map. So everything works if you add, if you have a moment map. All right? And also everything works replacing n by the dimension vectors for the quiver setting, for instance. Huh? So we have a more general setting. So I'm sorry I'm a bit late, so maybe I would like to finish with some open problems. So I already explained one. So the second is related to that, because you see in this picture, we only consider a moment map with respect to the action of GLN by conjugation. But you would like sometimes to consider other action of GLN. So it's a natural question to know what is analog, non-commutative analog for more general action. And this is a problem also for the Poisson reduction. Maybe you want to consider invariant not only with respect to the conjugation of matrices. So maybe to illustrate the problem, let's consider an example. So these come equipped with two commuting Hamiltonian actions. I just describe the moment map. So here, if you identify, maybe I just write G for the moment because I don't need its GLN. So here, it's just a projection for the first action, and here, maybe I have a sign minus. So this is a coagent action of H on X. And so now consider the case GLN. So what we have is that we have a non-commutative moment map like this, corresponding to the action of GLN over the representation space of this double Poisson algebras we have already encountered, but this corresponds to the moment map for the conjugation, and this is the sum of the two moment map. So it's natural also to consider a non-commutative moment map for independent action. So here we have natural candidate, but it's not clear what is Poisson reduction in this setting for the left and right action if you don't consider the conjugation. So here, of course, the example is easy, so we can have candidates, but it's not so clear how to generalize this. Sorry. Yeah, so I just illustrate. So let's consider this. So here you can consider the subalgebra generated by A, which is actually mu L. And here you observe that this gives you the invariant with respect to the right action. And so you can complete the cube as usual. Okay. And and you can similarly, if you consider generated by B, A, B minus 1, you get everything corresponding to the left action. So now you remember that this picture, we understood this picture also with vertex algebra analog. And this is nice because here you have a notion of chiral quantized moment map to that. And you can also take invariant. I don't define, but so here, because it's a right action, you have something like that. And here you recover your affine, maybe with a change of level. Does not matter. You have something like that. So everything commute and everything is compatible with the reduction in some sense. So if you combine the two problems, you expect that our notion of double vertex algebra should be compatible with the reduction. And another problem, I can say two problems? Yeah. Thanks. So sorry, I'm a bit fast, but it's open problem anyway, so not so precise. So of course, the notion of quantized chiral quantized moment map is very useful from B-heuristic reduction to construct double W algebras. So maybe another, so this was a problem 2. And another problem is, I remind you that the Zoos algebra of W algebras, let's say the universal one, is Slodovich slice, which are Poisson variety coming from G star. And in type A, it's due to Maffei that nilpotent Slodovich slice can be described in terms of quiver variety. Is not open problem because this is done. But the problem is, can we describe the Poisson structure from a double Poisson algebra? And this, if you combine with the first two problems, this could give double Poisson vertex algebra or double vertex algebra interpretation of OPEs for affine W algebras. And the last thing I want to comment is that the original motivation of van den Berg was to understand Poisson structure of multiplicative quiver varieties. And this is the original motivation to introduce all this machinery. But in fact, for multiplicative quiver variety, you need a double quasi-Poisson algebra. So, quiver varieties. So this you need double quasi-Poisson algebras. And so a natural question is, what are the vertex analog of quasi-Poisson algebras and double quasi-Poisson algebras? And the first problem in this, the first task in this problem is to understand what the jet algebra construction give you as a structure if you perform the jet algebra from this kind of structure. And if you can solve this problem and to understand what's become our cube in this situation, this should give you a Poisson vertex analog of multiplicative quiver varieties, which should be of independent interest. So, yeah, I think sorry for that.